All right, let's talk about bit manipulation. Honestly, it's one of those skills that can feel like a genuine superpower for a programmer. It lets you write code that's not just a little faster, but incredibly fast, super memory efficient, and lets you solve problems in ways that just seem, well, like magic. So let's get into it. So here's what we're going to cover today. We'll start at the very beginning, the language of computers, zeros and ones. Then we'll build up our essential toolkit with all the core bitwise operations. After that, we'll get into the really cool stuff, like how to represent an entire collection of items in just a single number. Then we'll take that power and apply it to some advanced algorithms. And to wrap it all up, we'll talk strategy for how to nail these kinds of questions in your next technical interview or exam.
First things first, the language of computers. Before we can start manipulating bits, we really have to get comfortable with what they are. How do they form the absolute bedrock of everything a computer does?
So let's just start with a really basic question. We see numbers, text, images on our screen all the time. But underneath it all, how does the machine actually represent a number? Because I can tell you, it's not with the digits 0 through 9 that we use every day. The secret is, of course, bit representation. Every single integer in your computer is stored as a binary number, just a sequence of zeros and ones. So for instance, in a language like C++, a regular int is usually a 32-bit number. That means a simple number like 43 is actually stored as this long sequence of 30 digits, which would look like 26 zeros followed by 101011. Let's actually break down how that works.
So how do we get from that string of ones and zeros back to our number 43? Well, it's actually pretty simple. Each position in the binary number represents a power of 2, starting with 2 to the power of 0 way over on the right. All you do is add up the powers of 2 for every single position where you see a 1. So in this case, we've got a 1 in the 32's place, a 1 in the 8's place, the 2's place, and the 1's place. You just add them up. 32 plus 8 plus 2 plus 1, and there you have it, 43. Easy as that.
Okay, here's something that trips people up all the time, and it's a huge deal for any exam. The difference between signed and unsigned integers. With a normal signed int, that very first bit, the one on the far left, is special. It's the sign bit. 0 means positive, 1 means negative. That leaves you with 31 bits for the actual value, giving you a range from about -2 billion to +2 billion. But an unsigned int doesn't have a sign bit. It uses all 32 bits for the value. So it can't do negative numbers, but its max value is way bigger. It can go all the way up to about 4 billion.
All right, so now that we know what we're working with, these zeros and ones, let's talk about the tools we can use to actually work with them. Think of these as the core operations in our bitwise toolkit. You've got to know these. Let's kick things off with the AND operator, which is just a single ampersand. What it does is it compares two numbers bit by bit, one column at a time. And the rule is simple. A bit in the result is a 1 only if the bits in that exact same position in both of the numbers above it are 1. So if you look at 22 and 26 here, you can see that only the first and fourth columns from the left have a 1 in both rows. And that's why our result, 18, only has 1s in those two spots.
And this leads us to a classic, and I mean classic interview trick. If you want to check if a number is even or odd, all you have to do is AND it with 1. So why does this work? Well, think about it. The number 1 in binary is just a bunch of zeros with a single 1 at the very end. When you AND any number with that, it zeroes out every single bit except for that last one, and that last bit determines if a number is even or odd. So if the result is 0, the number was even. If the result is 1, it was odd. It is insanely fast.
Next up, we have OR and XOR. The OR operator, that's the vertical pipe symbol, is a little more relaxed. It sets a bit to 1 if at least one of the corresponding bits is 1. Now, XOR, or exclusive OR, that's the little caret symbol, is much pickier. It sets a bit to 1 only if exactly one of the bits is 1. Check out the XO result for 22 and 26. See how it gives us a 1 wherever the two bits are different? That little property turns out to be incredibly useful, and we're going to see why in a bit.
Bit shifts are another incredible optimization tool. A left shift, that's the // basically just slides all the bits to the left and adds zeros on the right. Shifting left by k spots is the exact same thing as multiplying the number by 2 to the power of k. And a right shift, / does the opposite. It slides the bits to the right, chopping off the end ones. And that's the same as integer division by 2 to the power of k. These operations are way faster for the computer than doing actual multiplication or division.
Okay, so let's put these tools together into a little cheat sheet of formulas you should probably just memorize.
To mess with a specific bit, let's call it the kth bit, the first thing you do is create something called a mask. That's just a number that has only that one bit turned on. You make it by doing one Shift K. Once you have your mask, you can use OR to turn the bit on, you can use AND with the inverse of the mask to turn it off, or you can use XOR to just flip it. And please remember this C++ function, __ built-in pop count. It instantly tells you how many ones are in a number. It's an absolute lifesaver in competitive programming. All right, prepare to have your mind blown a little bit. We can take these simple operations and build something incredibly powerful. We can actually represent an entire set of things using just one single number. This amazing technique is called bit masking.
So here's the core idea. A 32-bit integer has, well, 32 positions, right? We can map each of those positions to an item. Let's imagine we have a set of items numbered 0, 1, 2, all the way up to 31. If the kth bit in our integer is a 1, that means item k is in our subset. If it's a 0, it's not. So a set like 1, 3, 4, 8 just becomes a single number where we've switched on the first, third, fourth, and eighth bits. This is ridiculously efficient when it comes to memory.
And this is where the real magic happens. All those standard set operations we learned in math class, they map directly to a single, lightning-fast, bitwise operation. You want to find the intersection of two sets? That's just an AND. The union of two sets? That's just an OR. It's the perfect combination of elegance and raw speed. Okay, so we've got the theory down pat. We have our tools. Now let's see how we can use this stuff to write code that absolutely flies and to solve some real, tough, algorithmic problems with huge performance gains. Let's take a problem like finding the Hamming distance. That's just the number of positions where two bit strings are different. Now, the normal way to do this is to loop through the strings and compare them character by character. It works, but it's kind of clunky. The bit-optimized way, it's pure genius. Remember how XOR gives us a 1 wherever the bits are different? So we can just XOR the two numbers together and then use our friend popcount to count up all the ones in the result. That's it. A whole loop becomes one beautiful line of code. And what's the payoff? Well, this isn't just a tiny improvement. We're talking about a nearly 30 times speed up. In a benchmark test, the normal loop took 13.5 seconds. The bit-optimized version, half a second. This is the kind of leap in performance that wins programming competitions and gets you hired. And now, for the final boss, dynamic programming with bit masks. Some problems seem to require checking every single possible ordering or permutation of a bunch of items. The thing is, the number of permutations, n factorial, grows so fast it's insane. For n equals 20, we're talking about a number so big your computer would never finish. But if we use bit masks, we can reframe the problem. Instead of iterating over permutations, we can iterate over subsets. And 2 to the power of 20? That's just over a million. A modern computer can handle that no problem. Let's look at a classic example, the elevator problem. We want to find the fewest elevator rides to transport a group of people. Instead of trying every order, we calculate the best solution for every possible subset of people. So what we do is we define a state, we'll call it best S, which stores the best answer for the subset represented by the bit mask S. Then we loop through all the possible subsets, starting with just one person and going all the way to the full group. For each person in a given subset, we look back at the solution we already found for the subset without them. And then we have two choices. Can this new person squeeze into the last elevator ride we calculated? Or do we have to start a brand new ride just for them? We take the better of those two options and store it as the best solution for the current subset. By building it up like this, one subset at a time, we eventually get the optimal answer for the whole group. Okay, that was a lot. So let's pull all of this together. How do you take all this knowledge and actually apply it when you're under pressure, in the middle of a tough interview or an exam?
If you remember nothing else, burn these 4 points into your brain. 1. Integers are just collections of bits you can play with. 2. Bit masking is your absolute go-to for handling sets efficiently. 3. That XOR and pop count combo is a secret weapon for finding differences fast. And 4. Whenever you see a problem that involves trying all permutations for a small number of items, your brain should immediately scream subsets and think about dynamic programming with bit masks.
So for your revision, you need to get your hands dirty. Practice converting numbers to binary and back on a whiteboard until you can do it in your sleep. Memorize those formulas for setting and clearing bits like they're your own phone number, and really train your brain to recognize the pattern of a bitmask DP problem. Finally, practice against the clock. Solving these problems fast comes from muscle memory. So, I'm going to leave you with this one question to chew on. Think about the code you're working on right now. Is there a loop, a check, a data structure that's secretly a bit manipulation problem in disguise?
What piece of your own work could you make 30 times faster with just a little bit of this kind of cleverness? Think about it. Thanks for joining me.